What is a perpendicular bisector? Well, if I have, let's make a line segment here. Choose tool line. Okay, if I have a line segment like so, and I bisect it, meaning I cut this thing in half. I'll just kind of glance at it since we're not doing constructions right now. Let's see, let's just go like that. I bisect that segment, and in fact I bisect it at a 90-degree angle right here. Then that is a perpendicular bisector. Now we have something called the perpendicular bisector theorem, and this says right here that any point on the perpendicular bisector of a segment is equidistant from the endpoints of the segment. Okay, what that is saying is if we have a perpendicular bisector here and I pick any point on it, let's pick right here, and I draw a line, oops, okay, that's not working. Try again here. If I draw a line from any point to the end points of the segment I bisected, then what this theorem is saying that these are equidistant, meaning they're the same length, they're the same distance. And that works with any part on the perpendicular bisector. I could start one right here, draw it to the end points, just like that, and these are equal distances. So that's all that theorem is saying. So I showed you what a perpendicular bisector is on a line segment, but we oftentimes look at them within triangles. So if I bisected all three of the legs of the triangle, then interestingly enough, all those perpendicular bisectors would meet in one point in the triangle. Let me show you. So I just kind of eyeballed it and drew all three of these perpendicular bisectors. This one over here, as you can see, bisects this line segment, meaning these sides are congruent, and it does it at a 90-degree angle. This one over here is bisecting this line segment here at a 90-degree angle, and this one over here bisecting this line segment at a 90-degree angle. And they do all meet always in one spot, and we call that the circumcenter. Let's write that down. It's not writing. Oh my goodness. Circumcenter. There we go. Now I often have students ask the question, okay, so circumcenter, is that the center of the triangle? Well, there's lots of quote-unquote centers of a triangle, but to be exact here, this is actually the center of a circumscribed circle around the triangle. Let me explain that. I'm just going to freehand this so it's not going to look good, but if I circumscribe a circle, aka draw a circle around this triangle, so it touches all of the vertices, that was bad, but you get the point, then that circumcenter that we found with all the perpendicular bisectors intersecting is actually the very center of the circumscribed circle. Okay, I got a better picture drawn for you here. So let's look at that whole perpendicular bisector theorem, but in regards to a whole triangle and all the bisectors in the triangle. Okay, so remember that theorem said, let's take a look at just this bisector we've got right here. It's bisecting this side over here at a 90-degree angle. Okay, so that theorem said that if I pick any point at all on this perpendicular bisector and I draw line segments to the end points of this side of the triangle that it's bisecting, that those two sides are congruent. Okay, so let's say, and I can do that on any of these. If I pick this perpendicular bisector, I could pick a point on it, draw line segments to the ends. Those would be congruent or equidistant, as they say in the theorem. All right, let's say that I pick the point right here. Let's pick that circumcenter. So notice if I pick that point and I do the same thing, I draw, oops, that should be right here. I draw lines to the end points of the segment. Oops, not very nice, but you can see that I'm drawing from that point, connecting it to the end points of the segment I bisected. Those have to be congruent by the theorem. Well, kind of turn your head and look at this bisector right here. Let's do the same thing. If I pick that circumcenter, that common point, and I connect it to the end points of the segment it's bisecting, then, and it shares one of these with the other bisector, then those are also congruent. Okay, let's look at the other one. If I've got this perpendicular bisector over here, I pick any point on it, but specifically we're going to pick the circumcenter, and I connect it to the endpoints. Well, it shares those with the other bisectors, then those have to be congruent. So what we see is if we find our circumcenter and we draw a line to each of the vertices, just like that, those all have to be congruent. And it actually makes sense because if you look at the circumscribed circle around it, well, what did we just draw? From the very center to the edge of a circle, that's just a radius. So each time you draw it to the vertices, you're also drawing the radius of a circle. So all of those have to be congruent. Let me make one more comment about perpendicular bisectors. As we saw in the last example, oftentimes we'll see the circumcenter in the center of the triangle, but that's not actually always the case. If you see over here, for instance, if you have a right triangle, like we do here, and then you draw all three perpendicular bisectors, they do still always meet in one point, but it does happen to be on the triangle itself. So the circumcenter in right triangles is always actually on the hypotenuse right here. Okay, and then you can still circumscribe a circle around it and it still follows all the same properties, but your circumcenter is no longer inside the triangle, it's on the triangle. And then we have another example over here. Your circumcenter can actually be outside of your triangle, and that happens if you have an obtuse angle. If you're dealing with an obtuse triangle and you draw all your perpendicular bisectors for all three segments, if you extend them, they do end up meeting, but they meet outside of the triangle, which seems kind of weird, but if you circumscribe a circle like I have drawn right here, to where it still hits all three of the vertices, it's just a really big circle outside, like further away from the triangle. But your circumcenter is still the very center of that circle. And then all the same properties apply. If I draw from the center to each of the vertices, like I did in my last example, so if I draw from here to each of the vertices, those are all still the same length. Because as you can see, they're each a radius of the circle. They start from the center, they hit the edge of the circle. Okay, and that was perpendicular bisectors in a nutshell.